Okay. Okay, we can start. I hope you have scanned the QR code, and I would like to start the course. So we will continue chapter 7, and probably today we will have at least two sections. I think we'll start with the partial fractions, and the other will be the I think we can go for improper integral. Okay. Okay, last time we have discussed the trigonometric substitutions, how do we apply, how we are using it. Basically, you need to just to look on which part that you are going to substitute. Okay, just a slight review. So whenever you have, for example, you have a constant, you have a variable, you can substitute with this 1 minus. You have a variable, you have a constant, you can substitute this uh, variable plus 1. Okay, you can substitute with the tangent squared. Like for example, you have variable squared minus 9. You can substitute this x with the secant, and then you can add some constant appropriately according to the constant in the equation. And you also can change the, for example, the constant minus variable. You can change this to sine or cosine. And also the last part is variable plus constant. You can change this x with tangent, which you are going to solve this, and you are creating basically this secant squared. Okay. Okay. Now the next section, this will be about the partial fractions. Okay. So to begin these partial fractions, I will give you the just illustrations. If you have okay, if we have this two fractions, we need to subtract these two. Usually, what we are going to do is we compound this denominator. We compound them. We multiply. So multiply this, right? And we write at the bottom, or maybe we can just write um, x minus 1, x plus 2, like that. And then this will be 2, x plus 2 minus x minus 1. We can solve this. 2x minus x is x. 4 plus 1 is 5. And then the bottom one we can just multiply. The compounds is x squared plus x minus 2. Okay. Now we have this fractions. We have this fraction that is a combination from 2 over x minus 1 minus 1 over x plus 2. So if you imagine, if we take the integral of x plus 5, if we have this, okay. Now if we can separate becomes the original fractions separately and take integral each of them. this will help, right? This will help, and the big chunk integral will be easy to compute, okay? So that's the idea of partial fractions. Okay? Why it's a method to help us calculate or compute the integral. So basically, to start with, to solve this, first I will just use some illustration to give you how we are going to do in most cases. So first, let me just write the fraction itself, and let's try to separate this into two. For example, we know that we can factorize this. We can factorize becomes x minus 1 x plus 2, as we did from the beginning, right? So first we do that. So we separate this becomes 2. Okay, and then we give this 2 in the top equations both a constant a and constant b. And then we try to find what is constant a and what is constant b. Okay, how to find that? First, we imagine this as we did in previous combinations. So we multiply, and this is the results, and the results divided by x minus 1 here becomes x plus 2, right? And then it needs to multiply with a. So we can write some equations regarding this, that is x plus 5 is equal a x plus 2 plus b x minus 1, right? Okay, now the next thing is we are going to compute ax, and we are then grouping all the variable and all the constants, right? So this will be ax plus 2a plus bx minus b. Okay, now what we are going to do from here, we solve this based on the linear equation of each component. So first, look on x. Okay. So first, we take this a plus b is equal 1. Okay, left and right should be equal. And then 2a minus b is a constant, right? So it should be the same as a constant 5. Okay, we solve this, find a and b. Solve the linear equations. You can use substitutions, you can use eliminations, whatever you can choose. I will just add this too. So we have a is 2, because a is 2, a plus b is 1, so 2 plus b is 1, so b is minus 1. So we could write this as 2 over x minus 1, and then minus 1, like that. And this is the same as we did as the beginning, right? Okay. So by doing this, then we can write down the integrations from the questions as 2 over x minus 1 dx minus, okay, and then we directly get the answer that minus 1 over x minus 1 is ln, right? So we can write this 2 ln x minus 1 and minus ln x plus 2 plus c. Or if you want to write completely, you can write, so this 2 can be here, we can write x minus 1 squared minus ln x plus 2 plus c, or ln okay, that's as an introduction for the partial fractions. Okay, we have several examples that might help, right, for partial fractions. But I hope at the very first introduction for the partial fractions method, I hope this clear enough of our objectives. What is the goal by using this method? So this method specifically for if you see a fraction like this fractions here, and you see that you can somehow uh, break down the fractions and make it into separate small fractions. That is the idea of a partial fractions method. Okay. Okay, if you have any questions, we can discuss before we continue. If you have, and I've seen uh, the your work on my questions last Friday because we don't have class last Friday, right? I think most of you are doing a good job. Okay. It doesn't need to be fully or completely like finishing all the questions. I just want to you just try which part you want you want to solve. I think most of you are doing a good job. But maybe later, if I have time this week, I will make an additional videos on another question that's similar from what we have in the Friday that I gave you. Okay. Uh, Maybe before we continue, I would like to just make sure the schedule. Uh, Today, 24 May, right? And we still have 27th of May, and then Thursday 1st of May, and then June 3rd is holiday, right? June 3rd is holiday, so we still have, uh, including this today, we still have one, two, at least three more class, um, and perhaps exam, the final exam, is probably around June after. Um, or do you want to early having in the 7th, June 7th, or June 10th is okay. I just want to know which one do you prefer? Do you prefer the June of 10 or 7th? So that's two schedule that I've offered. You can think. So June of 7 or June of 10 final exam. Okay, we still have, I believe, one more quiz, chapter 6, 7, and final exam. Okay, Julio, it's 7. Maybe anyone, if you have number 10 is fine. June 10, June 10. Okay. Okay, let me make wait a minute. Wait. Let me stop the sharing first. Do you see any? Wait. Okay. Let me see. Okay. Do you see polling in this in your system, in your WebEx? I create a polling system. Oh. Wait. Let me close again. Uh, wait. I need to edit. Uh, yeah, I forgot to edit the system. Yeah, I forgot to add the answer. Sorry. Again. Okay, now I think it's better. There are three students haven't choose. Can you choose? Uh, which one? We have two, one, two, three, four, five. Yeah, three students haven't choose. Are you there? I'm not sure which one haven't choose. Have you all choose? Who hasn't choose? There are three students haven't choose. It seems now still 50-50. Three students choose 7. Three students choose 10. Okay, I will open later. Okay, open again later at the end of the lecture. Okay, so let me just close this poll. Helen, have you opened the poll? Have you clicked the poll system? Okay, so I'm not sure who hasn't choose the results from the polling. So let me just close the poll and then open again later in the end of the lecture. Okay. So we still have this 33%, 33%. The other 33% is uh, not answering. So yeah. Okay. So later I will open again. Okay. Okay, let's go back to the lecture first. Okay, now let's continue. Okay. Okay, another case, or let me just write example on the partial fractions. Okay, if we have this, okay, and you see that the power is certainly is having more power than the denominator, the first thing that you can deal with this is we can construct polynomial divisions. Okay? We can construct polynomial divisions as I think you did in basic of math or maybe your high school. Okay? So we can construct this. And slowly we can take times to solve this. Okay, so we then get this as our result, and we have a reminder. Okay, we have a reminder. Now we can construct this fraction as x squared plus x plus 2 plus 2 over x minus 1. And of course, if we take the integrations, it will be easy, right? We can integrate each one of this, and we can integrate the last one as ln. So we can solve this by taking the big fractions into a small, or into a separate component, right? So it's basically we are using the polynomial behavior or characteristics. So if you have a functions of p over q, we can make it into some s, and this is r is q. The r is we call the reminder, right? So that's another idea for solving the integral, and this can be happen if the p degree is greater than the q, or equal also can be done, at least equal. Okay, now for more cases in the partial fractions, we will see through this p over q, p over q. So let's say case 1. If the q is a product of linear factors. Now we have some words for some definitions, but I believe not as much as important as the practical use. So you just see how it's done, okay? So if the q is, for example, you have a1x plus b1, a2x plus b2, and so on up until some k or n, bk, okay? So we can write the px over qx as, so if you have this as the denominator, you can factorize the functions like we did in the first example. We can take into each small fractions separately. Okay, and I think this is already been discussed at the very first example. Oh, another maybe just a review. If you have this integrations, what can we do here? We can check whether the function is factorizable or not. Okay. Now, if we decide to factorize, now look at this denominator. Okay. We could start with factorizing x. Right? We can have this. And my suggestions, okay, my preferred method to factorize this, because it's not x squared, it's 2x squared. And my way is taking this into a table. Okay, and this 2x squared, we can imagine maybe it's multiplication from x and to x, so we can write 2x and x. Okay, and then for minus 2, maybe this is 2 with minus 1, 2 minus 1. Okay, and then we can multiply and cross multiply. Minus 2x plus 2x should be 0, so it doesn't work, so we need to change to minus 1 and 2. So when we multiply these two, the first one is 4x minus x. Oh, it's the same as 3x, so this will be our choices. Okay, so we could have this as, so we could write x, 2x minus 1, and x plus 2. Okay, so we could write each of them as a over x plus b over 2x minus 1 plus c over x plus 2. And then you can have each integrations. Okay. And then the rest is to find a and b and c, and I think you can done it. Or if you would like to try, then we could start with writing x squared plus 2x minus 1 equal a will be 2x minus 1, x plus 2, right? And then plus b is x bx, x plus 2, plus c, this is x, 2x minus 1. Okay, and then we can solve. So this will be a, and then 2x squared plus 3x minus 2, plus bx squared plus b2, or plus 2b, plus 2c x squared minus cx. And we can combine all this. Okay, and then we can equaling both sides, so x squared should be equal 1, right? So 2a plus b plus 2c equal 1, and then 3a minus c equal 2, and then 2b minus, or maybe minus 2a equal minus 1. And then you can solve this and find a, b, and c. Okay, you can try by your own. Okay, but at least whenever you find a function that you can should be 2bx, 2bx. Oh yeah. Correct. So this will be 2b 3a plus 2b minus c. Yeah, correct. Thank you, Mission. Okay. All right. That's the case one. Okay, so this is the case number one. Okay, next sections. Let me move to the new sections. Okay. I hope you have writing at least the what's the case one is. Okay, the case two. We call the case two. We have the repeated linear factors. So this is when we have p over q as a1 over ax plus b1 plus a2. This is we have ax plus b1 and then squared and plus a3 ax plus b1 cube and then dots and some ax plus b1 and then the power of r. Okay, what does it mean? So it means that you can see that from the from the denominator, you can have a factors that is, you can arrange into the same factors, but we have a squared, cube, and then so on and so forth. Okay. So what does it do in the example? For example, if we have integrations, so we already see from here that it's having this cube. Okay, it's having squared here. Ideally, the first separation that we can think, okay, the first separations is if we can separate this becomes, or let me write in the bottom here. Let me write again the fractions. Ideally, we can simply separate becomes this is ax plus b. This is cx squared plus dx plus e. Okay. Ideally, this is the fractions that we can have. Okay. But what the repeated linear factors means in order to help our calculations, we are then going to separate this part, and this part becomes more small fractions. So we have smaller fractions in the whole. Okay. So this part here we can separate, becomes a x over x squared plus b over x squared, right? And we can simply cancel this, and we have a over x plus b over x squared. Now, by the same or similar method that we could think, okay, we could say that we might have, okay, from this part, we might have c over x minus 1 plus d over x minus 1 squared plus e x minus 1 cubed. And this should be perfectly having all in the top equation a constant. Okay, this is why it's so important, because this repeated linear factors, it can make this separate fractions as a perfectly constant in the top equation. Okay. Now, if you would like to check whether it's true, we could just take this cube and then divide with all the and this form we can just simplify it, and then it seems that we could just take it into our usual forms like this. Okay, but of course you will see that there will be some constant, additional constant here, that, oh, it's not similar. No, it's still similar, because this C, D, and E, it can be any number. It can be any number. This is just a simplification. So the same structure, it still has the same structure. We have the constant, and this is the variable. Okay, same structure. So the method, the repeated linear factors, whenever you find any squared, any cube, you can make a structure from a small power numbers. For example, so this one you can take it into integrations a over x plus b over x squared plus c over x minus 1, or maybe x minus 1 first, and then plus d x minus 1, and then squared, and then plus e x minus 1 cube. Okay, and then still we need to check and find what is a, b, c, d, and e. Okay. So from this separation, still we need to check. For example, we need to find a, then we need to write that x cubed minus x plus 1 is equal ax x minus 1 cubed. So it's having a cube, so it should be a little bit longer, plus b x minus 1 cubed plus c x squared x minus 1 squared plus d x squared x minus 1 and plus e x squared. Okay, and yeah, you need to have expansions, multiplications, and at the end we need to equally left and right. Okay, but I think this one a little bit long work. You have long work to do here. I just give you an idea for what we call repeated linear factors. Okay. Okay, any questions? This part, any questions? Okay, so case 1, you can factorize the denominator easily, and you can separate the fractions. Case 2, you have a repeated linear factors, and you can have perfectly constant for each linear factors. And then the case 3, we call irreducible factors. The irreducible factors. Let me move to, I think, the next sections. Okay. If you finish this part, I will move to the next section. Maybe I will wait for a few minutes, maybe 1 minute. All right, and move to sections. So case 3. So this is uh, if we have a qx. Let's say we have uh, a, a quadratic equations ax squared plus bx plus c, and if the b squared minus 4ac is less than 0, we call also this is as d, or determinant, right? This means that we will have a factor that is irreducible. Like you have the x squared plus 4, x minus 1. You know that the first one is x equal 1, but this one is it's not in the real numbers, right? So we call this irreducible factors. Okay? Irreducible factors. And still, we can still do some integration with this, at least the quadratic irreducible factors. We can still do something. So if we have, for example, x, and let's say x minus 2, x squared plus 1, x squared plus 4. And we can separate this, becomes the first one, x minus 2, is just a linear factor, so we have a constant. Okay. And the second one, we have the irreducible factor. So this is irreducible factor, this 2. Okay. So we can write, this is x squared plus 1. And what should we write in the first, the top equations is the linear equation. So we have bx plus c. Okay. Similarly, the last one we have also the linear equation. Okay. And how to solve this? How to solve this in the integration? So if we have integrations, let me write integrations, dx, integral dx, dx. How to solve is, we need just to remember, if we have 1 over 1 plus x squared, what kind of function that we can make it from this 1 over 1 plus x squared, okay, if we want to integrate. Or perhaps, before we integrate, what functions that we are going to differentiate, it will result in 1 over 1 plus x squared. This will be a tangent inverse, right? Or arctangent. So we can write this is the arctangent or tangent inverse x, right? So basically, if you integrate this, this will get you to tangent inverse x plus c, right? For this one. So let me write, maybe taking here. So if you have integrations 1 plus x squared dx, this will result tangent inverse x plus c. Okay. Now if we play with this functions, maybe we could take into x squared plus 4 dx. What can we do here? Now first, if we could imagine from the tangent inverse, if we are having this derivative of tangent inverse, if we play with the x, okay, this tangent inverse, okay, if we take the, for example, tangent inverse, and it's not x, but it's x over 2, okay, what will happen here? We have 1 plus, this is x over 2 squared, so we are having the same template, but we are going to have multiplication with half because of the chain rule, okay? The chain rule of x over 2, okay? We differentiate becomes half, and we need to multiply this two. So if we try to solve this, we could try to solve this, simplify these equations, I mean. So we could have 1 plus x squared over 4, this is 1 over 2. And we could take this as 1 plus x squared over 4 is, we could take it into, this is 4 plus x squared, right? So we could take this and make 4 plus x squared and multiply by half, cancel this 2, so we have 2 x squared plus 4, right? Now as we see from what we are having, we have this x squared plus 4, x squared plus 4, right? So actually we need just to multiply with half, right, to cancel this 2 in the top. So this will be resulting in the half tangent inverse x over 2 plus c. Okay. Now, of course, we need to make some general formulation for this. So we could take this into general formulations. That is 1 over, if we take x squared plus, let's say, a squared, okay, dx, this could have, by the same proving as we did in this x over 2, this x over 2 here, then we could have 1 over a tangent inverse x over a plus c. And how to solve the questions, how to solve this? How to solve this is basically we need to separate what you can solve is the one on the right, right? For the tangent inverse. The left one, we could say, probably we could take this use substitutions, right? b, let's say if b is x, this can be done with substitution, or any constant we have here for or negative, still we can do substitution, right? We can do the substitution method. But for c, this one, the right one, this could have something related to tangent inverse. Okay, I hope at least for overview, for the case 3, you can see that we are having why we are going to have the tangent inverse, because we have the irreducible factors. Okay, that's the reason. So the irreducible factors, because we can reduce the power, so we should have the quadratic irreducible or irreducible factors. Then we are going to involve the tangent inverse as in the answers for the integration. Okay, lastly, the case 4 for the partial fractions is just we have irreducible factors, but we have repeated. But it's still irreducible factors. So we are going to combine the repeated linear factors as the previous case with irreducible factors. It's actually still the same. So I hope you don't get confused on some words in this all the cases. You just need to focus on how to solve. Okay, for solving, remember, whenever you find the functions can be factorized, you need to factorize and make separations. If you can see any repeated linear factors, you can do repeated linear factors, okay, and you can have each perfect fractions, okay, with a constant on the top. And if you have irreducible factors, then you have the linear equation on the top, okay, and then later you can solve through tangent inverse and the substitution method. Okay, I hope that's at least for overview in general should be clear. Okay. Now the last case, the case 4. So we have the repeated linear, repeated, but it's irreducible factors. So, for example, we have the linear equation on the top, and the first one is we have the factors, and then we have the second part, and then until some r, and then r, and then this part is the irreducible factors. So we still treat like a repeated linear factors, but it's irreducible. And then the top equation will be a linear equation. Okay. So let me write fractions. It's quite long, the fractions. X cubed plus x squared plus 1. X minus 1. X squared plus x plus 1. And x squared plus 1 cubed. So these two, the last two here, this is irreducible factors, right? So first, we could take this. The first one is a over x, no problem with that. And then plus b over x minus 1, no problem with that. And then this third one, we have the irreducible, so we have cx plus d over x squared plus x plus 1. And the last one will become 3, three fractions plus ex plus f is x squared plus 1, and then gx plus h, x squared plus 1 squared, and then ix plus j, x squared plus 1 cubed. Okay, this is just for illustrations. Okay, it's an illustration. It's very long. If you would like, you can also try to find each component, but I don't think I will just give you in the exam. It's too long and it's wasting time. Right? But just to see some observations here, every irreducible factors will have linear in the top, the linear equations in the top, right? This is irreducible factors, irreducible factors, irreducible factors, all having linear equations. Okay. All right. Just to give you an overview. So here's for finish, and simply we can say partial fractions finish. If we have time, maybe we can have some practice, but I believe I will just continue, okay, just continue to give you more contents first, and then at the end we can have a big review for most of the content. Okay, maybe any questions? Any questions? Okay, maybe we have 5 minutes short break. Okay. I believe some of you still haven't scanned the QR code, right? So let me give you a QR code. Let me have a short break for 5 minutes. Okay, we can continue. Okay, any questions from the partial fractions? Okay, I hope everything clear. Clear? Clear enough? Okay, I think we can just continue to next section. Um, so this, I forgot to mention that this partial fraction is actually 7.4. 7.4 if you have a textbook. 7.5 is just a strategy. 7.6 also strategy using table of integrals. I will just skip these two sections. We just focus on later. We'll just show you some strategy directly from practice or exercise. But for now, we can focus on the 7.7, which is the improper integral. Is I think for 7.5 and 7.6, these two sections is just some additional that is basically just a strategy for the integral, not just not really a technique or any additional information. It's just some sections that explain how to use which techniques that you want to use or which part that you are going to integrate first. Okay, that's basically 7.5 and 7.6. Okay, what's the improper integral means? Okay, uh, I believe we explained before. Let me check. Oh, it's not 7.7, sorry. It's 7.8. 7.7 is just the approximations using the midpoint trapezoids. So I think I just skipped that. Okay. Recall that we define the integration from a to b of f of x dx. Okay. We deal with the functions defined on finite interval from a to b. Okay. And assume f doesn't have discontinuity. Okay. So what improper integral means is we will have infinite interval, first case, and the second case we have discontinuity. So we are going to break down what we have before as a rules that the definite integral should be having in the interval should be finite and it doesn't have any discontinuity. Okay. But now, why it's called improper? Because we deal with the infinite interval and we deal with the discontinuity. Okay, that's just for some overview. What will be our objectives? What is our goal? Okay, now to begin, let's start from the infinite interval. Okay, consider our functions is 1 over x squared. Okay. Let's say we are going to evaluate the area under 1 over x squared. Let's say from 1 until some constant t, and let me just put the illustrations probably here. Okay, for illustrations, this is what we are going to find: 1 t and then 1 over x squared dx. And by doing this integrations, we know that this will be 1 over x, minus 1 over x from 1 to t, and this will be resolving 1 minus 1 over t. So the area, this part, okay, is what we have, the 1 over 1 minus 1 over t. Okay. Now, if t is approaching infinity, okay, as illustrations, we might think that if we take the limit, okay, if it's getting larger, take the limit as t going to be infinity of our at. This means that we have limit 1 minus 1 over t. And we are going to look on the limit because it's going to have a large t, and we have 1 over t, so we can say that because it's 1 over t, then this will be going to be 0, right? This part is going to be 0, so we are going to have the result is just 1. Okay, so no matter what, the t, when you increase, getting large and large and large, the amount of the area, wait, not this, which one is this one? Yeah, the amount of the area, yeah, this is going to be just 1. Okay? So if we look on, it's good. 1 to 2, it's half. 1 to 3, it's 2 over 3. 4 over 5, and it's going to be keep increasing, and when your t is going to be having equal to or getting larger, getting to approaching infinity, your area just 1. Okay, this is also true from our confirmations from this calculations of limit. Okay, and it's true that it's going to be 1. Okay, so one idea here that is we can going through from this example, that we might take the limit. Okay, so we take the interval, okay, from 1 to some t, and we take the limit when t is getting infinity. The same thing happens when you have t on the bottom here, and this is a constant, maybe 1. So t, you can imagine, is getting negatively large, negative infinity. It is going to have the same strategy. Okay? Take the limit and evaluate the limit. Okay? When you have the results, then you have you are getting into something. You are getting into a finite number as the result of the limit. Okay? This might happen, and we can compute the improper integral. Okay, that's for the introductions of the infinite interval. Okay. If you have any questions, please can write in the chat box if you have anything to discuss. If not, then I will continue. And let me just compare 1 over x squared with another function, 1 over x. Okay, also this we call convergent. We say it's convergent. Okay, now let me give you, okay, this. So let's say we have another one that is 1 over x, and then let's just take it into our calculations from the integral. Let's say we have infinity 1 over x dx. What we can do to finish or to observe this is take the limit as t approaching infinity, and we take this 1 and t, and 1 over x dx. And this will be ln, and from 1 to t, and we could write this become ln t minus ln 1. So the result is just ln t, and t is getting infinity. So we see that from here, the integrations from 1 to infinity for 1 over x dx is diverged. Okay. So if we would like to check, okay, what is really happening with this 1 over x. Now let's see from the graph here. This 1 over x squared on the left, the gap point, the gap from the axis to the curve is really small. And when you move x to the right, okay, it's getting closer to the axis, right? It's getting closer to the axis, and seemingly we can say that at some point maybe we could just take it like the limit that we have, 1 over t, and 1 over t, you can make it as a 0. So we could say that, okay, the maximum area for this case is just 1, right? And now if we find this 1 over x, it's still having the gap here. We have a gap, and we say that when we increase the x to the right, we increase to the approaching infinity, we would find that it goes to be an infinite area. Okay, so by comparing these two, although it seems similar, we have different results. The left one we say it's converge, the right one we say diverge. Okay. And so by these two examples, we could take some general theorem for this infinite intervals. So we could say that in infinite intervals, let me write here, infinite intervals, if the integrations from a to t f of x dx exists for every number that t is greater equal a, or maybe we can write clearly, maybe over here, every number t greater a, then is equal using the limit and provided limit is exists. If limit doesn't exist, then it's probably a divergent. And same way, the second case is if we take t to b. So now we have from the left, it's getting negatively large. Okay. It exists for every number that b is greater equal t. Oh, let me take different color. Then or maybe this should be infinity. This should be negative infinity. Provided limit is exists. We say limit exists is convergent. If limit doesn't exist, then we call a divergent. Okay. And then another case that we might have is we can make a combination. So we could write if both same functions but different interval. So we have this both integral. They are both converge. Then if we have integration from negative infinity to infinity, this will be equal so we can separate the integrations if you have integral from negative infinity to infinity. And of course, a is a real number. Okay, that's some rules for the infinite intervals. Basically, to solve this is first you can divide by at least two parts. The first part is the integration part. Okay. The second part is the limit part. So you can do the integrations first, okay, as indefinite integral, just finding what's the integration of the functions. After you find the result, then you could input into the numbers that you are going to calculate, and then if it is improper, then using the limit for the infinite intervals. Okay, now the next sections, we will have the p test, okay, p test for 1 over x. Okay, so for example, if we have the integral from 1 to infinity, 1 over x with power of p. Okay, we would like to know for what values, okay, of p. Okay, so for what values of p, for what values of p that the integral converge. So what we are going to do is we are just taking the method that we have discussed before, and we are going to check is there any constraint for p to having a convergent value. So first, we could start with writing the integrations and then taking the limit so that we can. So I hope you understand. Okay? I hope you understand why we need to take the limit here. Okay, we need to take the limit because we have the infinite here. Okay, if we take infinite here, if we want to compute, forcing ourselves to compute this, it seems it's impossible, right? Because it's infinite. But if we have just a variable t, we can compute, right? So that's basically the reasons, the obvious reason. And actually, if you prefer to just solving integral first, you can just start integral the 1 over xp dx. As you can treat this as normal indefinite integral, right? Okay, so you can start here and find some value and plus c, and later you can input the infinite and 1 and then taking the limit. Okay, that's also okay. But let me just write with the limit here, okay, for just for your reference. So let me write in terms of x with power of negative p, and then we can integrate this x negative p. This will be x negative p plus 1, and then this will be 1 minus p, right? This is start from 1 to t. So we put t and 1 to x, so we have limit. So we could write 1 over 1 minus p. We factorize this, and we can, let me just write 1 by 1. Okay, 1 minus p. So this will be t 1 minus p, or we could write 1 over t p minus 1, right? Same thing. And then 1 we put inside is just 1, right? So we just take minus 1. So if we look here, we could have some possible uh, possible path. Okay? So if we look here, we could see if we take p greater 1, then we say that p minus 1 will be greater 1, right? So t will be getting infinity. And then p minus 1 also getting infinity, right? And 1 over p minus 1 is getting 0. Okay, that's for p greater 1. So for p greater 1, let me write here, for p greater 1, is equal 1 over p minus 1. Okay, and then the second path that we can have is if we have p less than 1. Okay. So we could start to construct. And so if this is going to be, so t is going to be or 1 over t of p minus 1, or this is t 1 minus p, this is getting infinity. So this is t getting infinity. So we have that the integral will be diverged. Diverges. Diverges for x less than 1. Sorry, for p. Now for p equal 1, we already did at the first sections, at the previous sections, is diverged, right? So we could divide this, becomes every p greater 1 convergent, and p less equal 1, this will be divergent. This is for integral 1 infinity 1 over x with power of p dx. Okay, any questions? So mostly this is the infinite interval. Okay. And the next section is supposed to be the discontinuity integral. Okay, I think we can continue a little bit just to show you the introduction of the discontinuity for the integral. Okay. this one and this one. Okay, this is what will happen in if we have discontinuity. Okay, for example, if we have the asymptote, the x equal b is our asymptote, so it's our asymptote. We call also the asymptote here, it's also asymptote. Okay. So what will happen in our construction in our integral? So let me just give you um, slide rules. Okay, so this is we call the discontinuity integrands. Discontinuity integrands. So first if functions continues on interval AB, and this continues at B, can I say B? Then this integral we can write as limit st approaching B from the left, okay, like from here, from the left, right, of a to t f of x dx. Okay. Now another one, if f continues on, oh sorry, this is supposed to be not, it's having open interval, and this continues at a, then the integrations will be limit st approaching a from the right. Okay. Now the third rule, okay, the third rule, and this is supposed to be, this two supposed to be the limit is exists. Okay, the limit is exists. And the third one, if the function has discontinuity C, this is in the middle here, like a figure 9 here, and A is less C less B. So we could have and the integral of from A to C of f of x dx and integral C to B f of x dx. They both converge. Okay, they both converge. Then or to be precise, it's supposed to be having a limit. We define this like usual integrations, and if this is having this continuity at C, then we just take the limit. Okay, take the limit. For A to C is going to be limit as C approaching from the left, so this is C from the left. This is for B is approaching from C from the right, right? Okay. Okay, and the rest is similar. Okay, we might have more exercise later on, but maybe giving you an exercise for this one, just to show you what will be in the calculations. So, for example, let's say we have integration from 2 to 5, 1 over square root of x minus 2 dx. Okay. Before we learn the improper integral, we don't really sure, but sometimes you just take this integrations, you calculate, and you have the numbers here, right? And you just take the 5 and 2, right? But if you take 2, we put here, it's discontinued, right? It's discontinued. So we need to be careful on that, and we need the limit, right? We need the limit to compute this integral. So first, we take the limit as t approaching 2 from the right. So we take this t to 5. Okay. And we integrate, this is as x minus 2 with half. So this will be having a plus 1, right? Minus 1, minus. So it should be half, and the rest will be also half, and this will be 2, right? So this will be equal to 2 limit of t approaching 2 from the right, 2 square root of x minus 2, and then t 5. So we could write down the limit 2, this is 2 square root of 3 minus square root of t minus 2. So this will be 0, so we could have this as 2 square root of 3. Okay, just a small example. Okay, I think I will just stop until here. We will continue a little bit small parts on this improper integral, and we would like to move to chapter 8, the last one. It's about the arc length and the surface area. And if we still have time, I think we still have one more class next week. That will be, I will just take as a review class. And as I mentioned before, okay, we would like to have a final exam. So let me open the poll again. So let me just stop the sharing first. Okay. If you have any question about this, you can reach out and maybe write on the chat box. But let me stop the sharing first, and let me open the polling. So do you want to have on 7th of June or 10th of June? Okay, okay, please choose your dates. Okay, I hope we can agree on votings. Okay. Okay, I think we can agree that from 15 students, 3 is choosing 7, 8 is choosing 10, 4 not answering. So 4, if we just look at the polls, I think 8 is the winner. So I believe 10th of June will be our final exam, okay, based on our polling. Okay, I hope everyone agree. Okay. 10th of June, so Friday, 10th of June, final exam. And how we are going to do this final exam, I will let you know later. We still have a quiz chapter 6 and 7. I will announce probably this week, maybe Friday night or Saturday morning. Will be only for 3 to 4 days. I will be opening the link 3 to 4 days. I will use the not the quizzes, but another platform. That is the same platform that I intend to use for final exam. So I hope everyone can have familiarity with the system. Okay. So I think I will just stop the class until here. If you don't have any questions, you can leave the meetings and see you this Friday, right? Okay. Yeah, you're welcome, Kim. Oh yeah, yeah. QR code. Wait. Okay. Okay. See you, everyone.